We have been talking about adsorption and we will continue on the same topic of adsorption. As I introduced in the previous class, adsorption is a surface phenomena. So you can have a gas getting adsorbed on a surface, a solid surface, or even a liquid in a solute can get adsorbed on a solid surface. So it is a surface phenomena, unlike absorption, where absorption is a bulk phenomena. So that is the main difference between adsorption and absorption. Absorption is AB, whereas adsorption is AD. So in absorption, a liquid gets the solute completely dissolved into it or absorbed into it, whereas in adsorption the solute gets covered on a solid surface. So there are different types of adsorption. One is called the physisorption or physical adsorption, the other is called the chemisorption or chemical adsorption. Both are different, especially with respect to the energies involved, especially with respect to the forces that are involved, that is the attractive forces between the solute and the surface. In the physisorption you have very weak forces, mostly van der Waals forces of attraction, so the energy is also very low. If you see that the delta H is of the order of 20 to 40 kilojoule per mole, and it also takes place at low temperature, that means below the boiling point of the adsorbate, whereas as the temperature keeps increasing the physisorption keeps decreasing. Whereas on the contrary, if you take chemisorption, the forces of attractions are chemical forces, sometimes it can even form a chemical bond, and that is why it is called a chemical adsorption or chemisorption. And delta H here is very high, almost 200 to 400 kilojoule per mole, and it can take place at all temperature. That means the solute can be in the vapor form also, unlike physisorption where the solute is below the boiling point. Okay, here when the temperature increases, the chemisorption also will increase, and then later on it will start decreasing. That means the solute that got adsorbed on the surface getting desorbed. Generally adsorption is always a thermodynamic equilibrium process, that means you can have adsorption or you can have desorption, that is the reverse of the adsorption taking place from the surface of a catalyst or a metal or an inorganic material and so on actually. So if you look at a typical adsorption isotherm, on the x axis you have the pressure, and on the y axis you have the amount of adsorbate or the solute that got adsorbed on a surface of the adsorbent of mass m. So generally as the pressure increases, the amount that is getting adsorbed per gram or kilogram or pound of the adsorbent will also increase, and after some time it gets saturated. That means further increase in pressure does not increase the amount of material or solute or adsorbate that got adsorbed. So this is generally an isotherm that is carried out at a constant temperature. So if you change the temperature you may have a different curve, but it will always follow the same pattern. It will initially increase with pressure, after that it will get saturated. That is why here we call the saturated pressure region, where you do not see any difference in the amount that is adsorbed even if you increase the pressure further and further. So at different temperatures you may have curves all exhibiting the same form. There are different types of adsorption isotherms. Generally we use linear adsorption isotherm or Freundlich or Langmuir, and BET is also used if you are talking about multi-layer adsorption, and all these three adsorption isotherms we generally consider it as a monomolecular layer. So the basic relationship, you have some adsorbate which is in the free form, it gets adsorbed on an adsorbent, that is an adsorption process, so you have the adsorbed species. Now the adsorbed species can desorb, so you have a vacant site available for some other adsorbate to get adsorbed. Okay, so you get a vacant site, so a vacant active site is necessary for this adsorption process. If you look at reactions like nickel catalyst hydrogenation, hydrogen has to get adsorbed on the surface of the nickel. If you are talking about some oxidation reactions on platinum catalyst, then the oxygen has to get adsorbed on the surface of the platinum before the reaction takes place, and so on. So the Le Chatelier's principle says that the direction of equilibrium will always shift so that the stress can be relieved. So if you are putting in pressure, the direction of the process will go from left to right. And also if you look at the left hand side, you have 2 molecules, and on the right hand side you have only 1 molecule. So always the equilibrium will shift and the number of molecule also decreases, because the adsorbate gets adsorbed on the adsorbent, so the number of degrees of freedom also decreases. Okay, so in based on all these principles, you can see that the equilibrium will always shift from left to right. Okay. Now adsorption is a very important phenomena, it is used in many places, it is used in purifying air, removing toxic gases, it is used in gas mask, it is used as a decolorizing agent in effluents like sugar effluent, silica gel which is used for removing moisture, that is as a desiccant in room purification system, alumina gels are also used. Then we use something called zeolites, zeolites are used in removing moisture, zeolites are used for many reactions, catalytic reactions. So adsorption is a very important phenomena and we have come across it in many different processes actually. So what are the factors that govern this particular adsorption? Temperature, pressure, surface area, activation of the adsorbent. So all these have an effect, and we will little bit try to understand the effect of each of these parameters. Okay. Temperature, for example, temperature has an effect and at the adsorption process, as I talked about before, especially on the chemical adsorption or chemisorption, there are temperature effects on the process. Similarly pressure has an effect on the adsorption process, and once the surface gets saturated, after the saturation pressure you will not see any more adsorption taking place. Surface area, more the surface area, more is the adsorption. So that is why you have activated charcoal which has several meters square of surface area per gram of the catalyst. So very small amount of catalyst will have large surface area. So higher the surface area, higher is the adsorption. So for adsorption you will always use high surface area material, whether it is alumina or carbon or zeolite or silica aluminates and so on. You will never use low surface area material here. Activation of the adsorbent, you have to activate the surface so that adsorption can take place. Sometimes we activate it by passing hydrogen, sometimes we activate it by passing acid, sometimes we activate it by increasing the temperature and so on actually. So there are different ways by which you activate. So these are the factors which control the adsorption process. So most of the industrial adsorbents fall into 3 categories. One is the oxygen containing compounds, that means generally they are hydrophilic material, they are polar like silica gels and zeolites. Then you have the carbon based material, that means they are hydrophobic or non-polar like your activated carbon, graphite and so on. Third type is the polymer based material. The polymers act as a matrix, especially if you look at ion exchange type of adsorption, you have the cations or anions anchored onto a polymer matrix. So these are the 3 different types of adsorbent used in the industrial applications. So let us look at some differences between the physisorption and chemisorption. In fact this table explains those differences. Physisorption, generally the forces of attraction are based on van der Waals forces. Chemisorption, you have chemical bonds or chemical interactions taking place. So these forces are weak, these forces are strong. That is why the enthalpy of the adsorption process also differs dramatically if it is a physisorption or a chemisorption. In the case of physisorption, the enthalpy is of the order of 20 to 40 kilojoule per mole, whereas in the chemisorption it is 200 to 400 kilojoule per mole. Physisorption generally is observed at low temperature, that means below the boiling point of the solute, and it starts going down with the increasing temperature. That means the physisorption process goes down with increasing temperature. Now chemisorption, if you take, it takes place at high temperature, that means the solute can be in the vapor form and the chemisorption takes place effectively. Physisorption is not very specific, whereas chemisorption is highly specific. So I can just remove one single gas from a mixture of gases. That is the main adsorption of chemisorption process. If you take physisorption, generally you can have multi-layer of the adsorbate on the surface of the adsorbent, whereas in chemisorption generally it is a monomolecular layer. Physisorption is reversible, chemisorption is irreversible. So these are the differences between physisorption and chemisorption. So you can have the same solute or same adsorbate adsorbing on the surface of an adsorbent, either as a physisorption based process or as a chemisorption based process. So if you look at the adsorption kinetics, it will look almost like a normal chemical kinetics. You have the rate of adsorption on the left hand side and there is a constant here, that is called a rate constant. Just like chemical reaction, we have a chemical rate constant, here also you have a rate constant. Then we have P, P is the partial pressure of the solute which is getting adsorbed, and X, that is the exponent or kinetic order. See, it is exactly like your chemical reaction. Okay. So the rate of adsorption of a molecule on a surface is directly proportional to the pressure raised to the power some exponent value there. Now we can bring in the Arrhenius term, exactly like chemical kinetics, we can bring in the Arrhenius term, we can bring in the pre-exponential term as well, or the frequency factor term. So if you bring in that, we have the constant being replaced by A into exponent minus EA by RT multiplied by pressure raised to the power X. So E is the activation energy for the adsorption process, R is your universal gas constant, and T is the temperature in Kelvin, and A is your pre-exponential factor or pre-frequency factor or collision factor. So there are different names for A. So the rate of adsorption is given by this particular term. So it looks exactly like your chemical kinetics, and the rate of adsorption is governed by mainly two factors: the rate of arrival of molecule to the surface. So you have molecules in the bulk and then you have the surface like a metallic surface or a oxide surface. So the rate of at which these solutes or adsorbates arrive at the surface of the adsorbent, that is one term, and then the proportion of incident molecules which undergo adsorption. So just because they come near the surface or they hit the surface does not mean they get adsorbed, but there is always some proportion out of which the bulk of the molecule which come to the surface will get adsorbed. So there are two terms. So there is something called the sticking probability that will come into the picture. So the rate of adsorption per unit area of the surface, because adsorption is always per area, is a product of incident molecule, that is the flux, and the sticking probability. That means a molecule, just because it hits the surface does not get stuck to the surface. So there is always a probability. So the sticking probability, and just like any probability term, it will vary between 0 and 1. So the rate term, we have it as number of molecules per meter square, that is the surface, and because it is a rate term, we have per second or per time, something will come there actually. So rate of adsorption is equal to the sticking probability into the flux. Now if you have the flux of incident molecules is given by the Hertz-Knudsen equation, So the flux F is equal to P is your gas pressure divided by 2 pi mkt raised to the power half. T is your temperature in Kelvin, m is the mass of one molecule, k is your Boltzmann constant. So this is the flux which can be substituted in this rate of adsorption equation. So as I said, the sticking probability, because it is called a probability, it will always vary between 0 to 1. So the lower limit will be 0, that means nothing will get stuck, and it can have the highest number as 1, that means whatever comes and hits the surface of the adsorbent will get stuck. So you can have either 0 or you can have 1, and it depends on the existing coverage of the adsorbed species theta and presence of any activation barrier to adsorption, because there is always certain barrier the molecule has to overcome before it can get stuck to the surface. So there could be an activation barrier. So we can have a relationship like this: sticking probability is equal to f of theta multiplied by exponent minus Ea by RT. Ea is your activation energy for the adsorption process, that is the activation barrier which I talked about before, and f theta is a function of the existing surface coverage. So the sticking probability depends on the amount of surface coverage and presence of any activation barrier. So you have two terms, one is the function of the existing surface coverage, that is represented in the first term, and this is the activation barrier which the molecule has to overcome so that it can get adsorbed from a free state. So the rate of adsorption, if you put in all these terms here, you will end up with rate is equal to f theta into pressure exponent minus Ea by RT divided by square root of 2 pi mkt. So you see the rate of adsorption can be defined in terms of certain fundamental parameters. Ea is your activation barrier which the molecule has to overcome, number 1. T, that is the temperature at which you are performing. P is the pressure of adsorption, and f theta is the existing surface coverage. So as the surface coverage increases, the rate of adsorption will go down. As the surface coverage is very low, the rate of adsorption will be very high. So you see this equation for adsorption can be derived based on the Knudsen equation. Physical adsorption, as I said, will be decreasing as you increase the temperature, because it is a very weak forces and it is physisorption, and it is generally happening below the boiling point of the solute. So x by m, where x is the amount of adsorbate or solute which gets captured by the adsorbent, divided by m is the amount of adsorbent. So it goes down like that. So if it is a chemical adsorption, initially it will go up and then later it will fall down. So initially as you increase temperature, the amount adsorbed goes up, whereas later on as you keep increasing temperature, the amount adsorbed goes down. Now I introduced 3 types of adsorption isotherm before. Let us spend more time on that. We will look at those equations and see what is happening. The 3 types of adsorption is linear, Freundlich and Langmuir. So linear, as the name implies, is a linear relationship between the solute adsorbed and the concentration of the solute in the bulk phase. Okay. So Q is equal to K into X. Q is the amount of solute adsorbed per amount of adsorbent. Okay. X is the concentration of the solute in the bulk phase. So there is an equilibrium that is taking place between the X, that is the concentration of solute in the bulk, and the concentration of the solute in the adsorbed phase, and K is the equilibrium constant. So this is called a linear relationship, understand. So according to this linear relationship, as x increases q will keep on increasing. So if you look at the x axis here, the solute concentration in the solution, and this is the amount of solute adsorbed per amount of adsorbent, it will keep on increasing in a linear fashion and it will pass through the origin. So that is called a linear relationship. Generally it will not keep on increasing infinitely, because after some time the surface has to have some sort of a surface coverage, and it will prevent further adsorption, but at up to certain concentrations of solute in the solution you will find a linear relationship, and it becomes easy for you to perform certain calculations if you assume a linear relationship between q and x. So here q is the solute concentration adsorbed on the adsorbent, and x is the solute concentration in the solution. So there is a equilibrium between the solute in the adsorbed phase and in the bulk phase, and k is that equilibrium constant. Now let us look at another adsorption isotherm, that is called the Freundlich, which is given by a curve like this. So here q equal to k x raised to the power n, again you have a k which is the equilibrium constant, but here the difference is you have a term called n. N can be greater than 1 or it can be less than 1. So if n is less than 1, we can say adsorption is favorable. If it is greater than 1, then we can say adsorption is not favorable. So the graph also will be like this, or it may be in a different form actually depending upon the value of n. So here I have drawn a graph for n is smaller values. Okay. So the Freundlich isotherm gives a non-linearity to the adsorption isotherm, where the adsorption isotherm relates the solute concentration in the adsorbent phase and in the bulk phase. Q is what the solute concentration in the adsorbed phase, and x is the solute concentration in the bulk phase or the solution phase. Now let us look at the third adsorption isotherm, that is given by the Langmuir adsorption isotherm. So what happens here, the solute concentration in the adsorbed phase increases as I increase the solute concentration in the solution, and after that it saturates, it plateaus, it remains constant. That means the number of sites available for adsorption of the adsorbate in the adsorbent reaches S saturation, there are no more sites available. So even if you increase the concentration of the solute in the solution, it will not get adsorbed, that is why it will sort of flatten out. So initially it looks like a linear relation, and after that it flattens out, you see that. So initially it is a linear, and then after that further increase in solute concentration in the solution will not have any effect on the concentration of the solute found on the adsorbent. And this equation is given like this: q equal to q naught into x divided by some constant k plus x. So if you look at this equation, at very small x values, this denominator we can neglect this x, so you will have x only in the numerator, so it will look like a linear relationship between q and x. So at very low x values it is like a linear relation, q is directly proportional to x at very low x values. Okay. At very high x values, if we neglect k, this x and this x will cancel, so you will end up with the constant. That means at very large x values q will not depend on x, so it is like a zero order reaction. That means very large x values your q will be constant, it is a zero order reaction. So at very low x values, when the x is very small, you will have q directly proportional to this x. So q and x are related as a first order relationship here, and at very large x values these x's will cancel, so q will be a zero order relationship with respect to x. That means increase in x will have no effect on q, So this represents a first order relationship between Q and X, and this represents a 0 order relationship with respect to Q and X. This happens at very large values of X because your surface is getting saturated, there are no more vacant sites available for the adsorbate to come and adsorb on the surface of the adsorbent, and this type of relationship is mostly more realistic when compared to your linear or Freundlich, and generally these relationships are reasonable at very low concentrations of X, but at very large concentrations of X I think I would say you can assume the relationship between Q and X to follow some sort of a Langmuir isotherm. But the most important assumption you need to remember in Langmuir is that it is a monolayer adsorption. That means once the site is occupied by one adsorbate, you cannot have another adsorbate sticking on top of it. So it is a monolayer adsorption process. So that is the main assumption in the Langmuir adsorption isotherm derivation. Now let us look at different types of adsorption process, how a chemical engineer will look at, because a chemical engineer is used to process type of approach, and you will look at different types of process. You can have batch adsorption, you can have a continuous adsorption, and so on. What happens in a batch adsorption? What do? You take a adsorbent and then you add it to a solution containing the adsorbate or the solute which you need to adsorb, mix them both thoroughly and then let them reach an equilibrium. You filter out the adsorbent and hopefully the solute would have got adsorbed in the adsorbent. The solute could be a toxic waste, unwanted chemical and so on, or it could be a protein of your interest or a metabolite of your interest. So in a batch process what you do is you mix the adsorbent and the bulk solution which contains your adsorbate, mix it up thoroughly, then filter it, and then you may have to regenerate your adsorbent so that it can be again reused. Then how do you regenerate? If it is a gaseous type of reaction you can heat it up, so hopefully the adsorbate will get desorbed and the surface is available, or you can use an activating agent. Sometimes you may use a concentrated hydrochloric acid, or you may use oxygen gas at high temperature. For example, if you are using oxygen gas at high temperature, it will burn away the chemicals or waste material that has adsorbed on the surface into CO2, that way your surface will be again available for further adsorption. Or you can reduce the pressure so that whatever has been adsorbed can get desorbed. So these are the activation. So in a batch process you have two sets of operation, one is the adsorption operation, other is the desorption operation where you are regenerating your adsorbent, and now the adsorbent is available for further adsorption. So when you mix the adsorbent into the bulk, your solute gets partitioned between the adsorbent or in the bulk, okay, that is your K, the constant value which comes into picture actually. So this process is bit slow, it is a time consuming because you need to do the adsorption and then you need to do the desorption or regeneration, again you go back to the first step. So it is a slow process and time consuming. Batch process is always slow and time consuming actually, but it is very easy because you just need a vessel, you take your solution which contains a solid that needs to be adsorbed, you add your adsorbent, mix it, and then you take it to another filter or another vessel where you are separating it out, then you can take it to a third vessel where you are regenerating your adsorbent and again bring it back to the first vessel. So that is how you keep doing this operation. It is a manual operation because you need to mix them, remove them, filter them, regenerate, again mix them and so on. Let us look at the mass balance in a batch adsorption process. Suppose if I want to design a adsorption system I need to know how much adsorbent I need to take to remove certain percentage of a toxic metabolite or a solute, okay. So I need to decide on that, or if I know I am going to add certain amount of adsorbent, how much of this solute will get removed. So if I want to do both these type of calculations, all I need to do is a mass balance. The concept, the principle is very simple, you just do a mass balance for the solute, that is all. So here we have a stage, you are adding a feed solution which contains XF concentration of the solute that needs to be adsorbed, okay. Then you are adding the adsorbent, that is the solid. So imagine your F is a liquid and W is a solid, the solid may contain certain concentration of adsorbate. If you are adding a fresh adsorbent, then of course QF will be 0, but if you are using an old adsorbent, it may contain some of the adsorbate present here. So there are two inputs and there are two outputs, the one output is your bulk solution F, so the same amount of F that is entering is leaving, but the concentration of the solute or the adsorbate here would have decreased because some of the adsorbate has been adsorbed. So if you look at the W, that is your adsorbent, the amount will be the same, W here and W there, but it would have picked up some solute. So here Q will be greater than QF, whereas here X will be less than XF because some of the solute or the adsorbate has been transferred to the adsorbent. So there are two inputs, two outputs. So what do? We take a concentration of solute in here plus concentration of solute in here, that should be equal to concentration of solute out in this stream plus concentration of solute out in this stream. So there are two inputs, two outputs, and this is what this equation represents. XF into F is the amount of solute coming in through this stream, QF into W is the amount of solute coming in this stream. This should be equal to X into F, that is the amount of solute leaving in this stream, and Q into W, that is the amount of solute leaving in this stream. This stream is because of the adsorbent, and this stream, these two streams are because of the solution or the bulk liquid which contains your adsorbate. So the bulk liquid is losing some adsorbate which is taken up by the adsorbent, that is what this equation is. So here XF is your concentration of your solute in the feed, QF is the concentration of the solute in the adsorbent, X is the concentration of the solute that is leaving the feed, and Q is the concentration of the solute in the adsorbent that is leaving the stage. So this is a single stage mass balance. So knowing certain terms we can calculate the unknowns. So F is the quantity or the amount of the feed solution, it could be in liters per minute or meter cube per minute, okay, or cc per minute, and W is the weight of the adsorbent that is getting added, it could be in grams, kilograms, micrograms. So you can see, so the units, please note the units of X and Q should be corresponding to that. So if you have F in liters, so X will have micrograms or grams or kilograms per liter. So if W is in kg or grams, then your Q will be some concentration per gram or kg, so that they all match, the units have to match, because F is in volume, you will have X will have a denominator volume term, and if W is in weight, Q will have a denominator in weight term. So we can rearrange this equation, mass balance equation, to get Q equal to QF plus F divided by W multiplied by XF minus X. So XF is the concentration of the solute in the feed solution, X is the concentration of the solute that is leaving in this solution of flow rate F, and W is your amount of adsorbent added, QF is the initial amount of solute present in your adsorbent, and Q is the amount of solute that is present in the adsorbent that is leaving the stage. Generally QF is 0. If I am taking a fresh adsorbent, there will not be any solute present, so I can neglect this term QF term, and Q will be equal to F by W into XF minus X. Okay. This is called the operating line, because if I plot a graph where x axis is x is the solute concentration in solution, and y axis is q is the concentration of the adsorbate in the adsorbent, there will be, this will be a straight line, this equation, okay, and this is called the operating line. So if you take a continuous stir tank, so far we looked at the batch process. So in the batch process what we are trying to tell is, in a batch process you have two streams entering a stage, okay. One of the stream contains your the bulk solution where the solute is present or the adsorbate is present, then you have another stream where you have the adsorbent which may or may not contain the solute. When you bring both of them together, mix them thoroughly, let them allow it to reach an equilibrium and separate them using a filter. We are using a filter because we assume the adsorbent is a solid, like an activated charcoal, or it could be a zeolite, or it could be a silica gel, it could be a silica alumina and so on. So by separating it out, the solute has transferred from the bulk solution into the adsorbent. So we do a mass balance of the solute present in 4 streams. What are the 4 streams? The stream 1 is the feed solution, stream 2 is the fresh or used adsorbent that is added, stream 3 is the bulk solution that is leaving, so it has lost some adsorbate to the adsorbent, and stream 4 is the adsorbent that is collected after filtration, okay. So some of the adsorbate has moved or got transferred from the bulk solution to the adsorbent. So that is how a batch process works. So what I can do, suppose if my adsorption efficiency is not 100%, I have achieved about say 60 or 70%. Now I take this solution, take it to another vessel where again I add some adsorbent, again I do a adsorption process, and again I remove some of the solute. So I may have multi-stage adsorption taking place, maybe 1, 2, 3 stages. So I will do in the adsorption where I add the solid, then I will do a filtration, then again I will do an adsorption process where I may add some more solid, and again I may do a filtration. So you may have more than one stage, that is possible actually, so that you remove as much of the solute or the adsorbate possible from the bulk solution. And especially if you are interested, if it is in an environmental type of situation where you do not want the toxin present at all in your water leaving, then you do this operation many times until the concentration of the toxin comes down to ppb or even very small or negligible. Or if there is a situation where you would like to recover a protein of interest, so you do not want any of the protein to go away with the bulk solution, you may carry out this adsorption stage 2, stage 3 and many stages until whatever protein is present in your bulk solution has been totally adsorbed. So that is how you do in a batch process. Now let us look at a continuous process, where as the name implies the adsorption process is continuous. So in a continuous process what can happen, you may add your feed solution or the bulk solution continuously. This feed solution may contain your solute or adsorbate at a concentration of XF. Now you have a tank containing your solid which is the adsorbent, like it may have the activated carbon inside or the zeolite inside. So the solution comes in, they get mixed thoroughly here, because there is a residence time here, the solute gets adsorbed by the adsorbent. So the solution that is leaving will have a concentration of the solute X, here X will be less than XF. So during that residence inside, the solute gets transferred from the bulk phase to the solid phase. So there is always a residence time in this process, and what is the residence time? We can calculate the residence time if I know the volume of the tank and also the feed solution. So if I do V divided by F, that gives you the residence time of the solution inside the vessel, adsorber, as you call it, adsorber. The most important thing is the solution that is leaving the tank should not carry the adsorbent as well. So generally you will have a filter unit present here, so that the solids are retained and kept inside your vessel and they do not get transferred and travel with the liquid that is leaving the tank. So this is how a continuous stirred tank adsorber works. So you can adjust your residence time so that the adsorption is efficient, or there is a equilibrium that will be reached between the solution that is leaving the vessel with the solids that are present inside the vessel. So what are the advantages, disadvantages with a continuous adsorber? We can continuously process some fluid, that is one advantage, but one disadvantage, as we keep on mixing, the solids may start breaking down into smaller particles and they may start traveling and leaving the adsorber with the effluent stream or the exit stream. So that could be a disadvantage. That you assume that the liquid that is entering reaches an equilibrium with the solids that are present inside. So your residence time has to be sufficient so that they reach an equilibrium. So you need to keep that also in mind actually. So we can also do a mass balance for the continuous stirred tank adsorber as well. So what are the things happening in a continuous stirred tank adsorber? There is a feed entering, that is the bulk solution that is entering, which contains your solute. XF is the concentration of the solute in the feed, X is the concentration of the solute leaving. So F XF minus X is the concentration difference which has been taken up. Okay. Now this minus 1 minus epsilon V are adsorbed, this is the amount of solute that gets transferred to the adsorbent, where here epsilon is the voidage. Okay. So V is the volume of the vessel, R is the rate of adsorption process. So this is the mass balance on the right hand side. Now this should be equal to the accumulation. So here we are talking about input minus output minus amount getting adsorbed from the liquid phase into the solid phase. Okay. So this is the input minus output leaving the vessel, that is material coming into the vessel, material leaving the vessel, minus the material that is getting transferred from the liquid phase to the solid phase. This should be equal to the amount that is getting accumulated inside the vessel. So what is accumulated inside the vessel? So epsilon into V, this is the amount of the liquid present inside the vessel, multiplied by dx by dt, where x is the concentration of the solute in the bulk inside the vessel. So this is the amount accumulation, E into V dx by dt. This is the amount of the solute entering the vessel because of the flow fluid, and this is the amount that is leaving the vessel because of the flow of the liquid flowing out, and this is the amount that is getting adsorbed from the solution phase or the bulk phase to the adsorbent phase. Okay. So epsilon is the voidage, so E epsilon into V gives you the amount of liquid present inside the reactor or the adsorber. 1 minus epsilon into V tells you the amount of the liquid, that is epsilon V. 1 minus E into V gives you the amount of solids present in the vessel. So epsilon into V tells you the amount of liquid present inside the vessel, 1 minus epsilon into V tells you the amount of solids present in the vessel. So this is called the mass balance, entire mass balance, and if you want to solve this particular equation we need to have some initial condition, right. So initially the vessel will not have any solute present inside. At time equal to 0 your solute with the solution starts flowing inside. So whatever adsorbed initially at time equal to 0 will be 0, and then slowly there will be a build up of solute inside the vessel as well as in the exit stream. So you can solve this first order differential equation, and by doing that we will be able to calculate what is the effect of time on the concentration, that is x, that is the concentration of the solute that is leaving the vessel. So in order to do that we need to still consider many other terms. For example, we need to have an equation for the R adsorbed, okay. We need to have an equation for the R adsorbed. So we can assume a mass transfer type of relationship. All chemical engineers will know what is mass transfer. So it is a very common term because you are going to have the solute present in the liquid phase moving into the solid phase. So we can have a term like this where R adsorbed is equal to KL into A into x minus x star, okay. So KL is the mass transfer coefficient, A is the surface area of adsorbent per tank volume, x minus x star where x star is the concentration in the solution which should be in equilibrium with the adsorbent, okay. This is the driving force and this is the area and this is some constant. So these three terms together gives you the rate of adsorption, and if it is a linear adsorption isotherm like as we saw before, Q can be is equal to K into x star. So we can instead of x star put it as Q by K here. So here instead of R adsorption we can write this particular equation, and instead of x star we can write it as Q by K. So once you have these terms included into our first order differential equation, it becomes very simple for one to solve. Let us not go into the solution of this first order differential equation, but if you solve this first order differential equation you will end up with the equation of this form: Q by K xf is equal to 1 minus, there is a E raised to the power minus sigma 1 t, there is a E raised to the power minus sigma 2 t. So E power minus t will always have an exponential type of decaying function actually, where sigma 1 and sigma 2 is given by this particular equation, and B that is present inside this equation is given by this. So you can see quite a simple relationship which connects the Q, that is the amount of solute that gets adsorbed onto the surface as a function of time, okay, with all the basic parameters like flow rates, the volume of the tank, the voidage factor, the K which is the partition between the liquid and the solid phase, KL is the mass transfer coefficient, small a is the interfacial area and so on actually. So you have all the basic design terms relating between a t, the time, and the q. So how will the relationship will look like? So as the time increases, initially q will go up because initially you have fresh adsorbent present inside your tank. So as time increases, the value for q will start from 0 and then go up and get saturated. So after that you will not be able to allow the same adsorbent to adsorb any more fresh solute or adsorbate. So what do you have to do? We need to stop the process and regenerate your adsorbent, or we need to add fresh adsorbent and so on actually. So again as time increases, the x of minus x initially at time equal to 0 it will be here and then it will start going down and it will reach a plateau here actually. So after some time your adsorbent gets fully saturated with the adsorbate. So as I said, we need to do some sort of a regeneration of the adsorbent, or we need to add fresh adsorbent. So these are the two different ways by which you can increase the adsorption of the solute. So we looked at two different types of operating conditions. One is the batch type of adsorption, other one is the continuous type of adsorption. In the batch type, what do? We take the adsorbent, that is the fresh adsorbent or used adsorbent, that is a solid, then mix it up thoroughly with your bulk solution which contains your adsorbate, and then you filter it. So by doing this you have transferred some of the solute or adsorbate present in the bulk to the adsorbent. So once you have transferred, you can desorb and again regenerate your adsorbent and again put it back for further recycle. Whereas in a continuous process, what do? You have a stirred vessel, you have the adsorbent present all the time inside, the liquid flows in and the solute that is present or the adsorbate that is present gets adsorbed. So when the liquid goes out, the concentration of the solute going out will be much less than the concentration of the solute that is inside the vessel. Okay. So how did we model it? Here we have something like a first order differential equation. So input minus output minus the amount adsorbed will be equal to the accumulation. So this is a very standard mass balance relationship. So by taking that, by assuming that the rate of adsorption follows a mass transfer type of process, and if you assume a linear relationship, we can have an analytical solution for the adsorption process as a function of time. But if you have a non-linear relationship for the adsorption isotherm like a Langmuir type of model, then you will not be able to get a simple analytical solution, but you need to use some sort of a numerical package to solve this entire differential equation, because it becomes slightly a non-linear type of differential equation rather than a linear type of differential equation, but it can be solved using a MATLAB or any other differential equation solver type of package. So we can get a relationship between the rate of adsorption process depending upon the flow rate into the stirred tank as well as the volume of the stirred tank. So we can manipulate and we can change the adsorption process.